All right, guys, this is Mrs. Lyons, and here we go on page 7. And we may try to do 7 and 8. We will see. We'll do at least part of 7 and 8. Because 7's pretty quick. Now, 7 starts with something that we did not talk about. And there's one question on the test about oxidation and reduction. Okay. What happens in oxidation reduction is one of the elements, okay, let's write this down, one element will lose electrons. And one element will gain electrons. Okay, and I got this little gimmick to help us remember. One of these is oxidation, one of these is reduction. Okay, and the way that I remember it, and you'll see me do this, is I use this little what do you call them? Acronym, mnemonic device. Leo, the lion, goes grr. Okay, so here's what this means. Leo is lose electrons, and that equals oxidation. Grr is gain electrons, and that is reduction. Okay, so when we look at an equation, a chemical reaction, okay, anytime, and this is something that maybe it will make sense because you kind of know it, we just haven't talked about it specifically. When you have an element by itself, not part of a compound, it's not an ion, it's an element. So it has a charge of 0, okay? When we have elements that are part of compounds, we know that those are ions and they're going to have charges. For example, we know that the chloride ion has a -1 charge. So in this case, copper, because there's 2 chlorines, copper would have to have a +2 charge. Okay, so when this single replacement reaction takes place, here's what happens. Remember, silver is going to bump copper out, and we're going to end up with silver chloride and copper by itself. So copper becomes an element with a 0 charge, and silver is now connected to chlorine. Chlorine still has a -1 charge. Silver now has a +1 charge. Okay, so now think this through. Whoops. Okay, silver over here has a 0 charge. How does it end up with a +1 charge? Silver loses an electron. Okay, and from losing, remember electrons are negative, so losing an electron, it gains a +1 charge. So loses an electron is oxidized. So that means silver is oxidized. And copper, see what happens to copper? Copper has a +2, is a +2 ion in the reactant side. In the product side, we have copper element, copper atom with a 0 charge. The way that happens is copper gains 2 electrons, okay? Gains electrons, reduction. Okay, so in this equation, the silver is oxidized, the copper is reduced. Okay, again, there is one question on the final about this, so maybe this will give you just enough information to make an educated guess. All right, let's look at the second one. Okay, so we have barium sulfate, and potassium. So potassium element by itself has a 0 charge. Okay, same thing over here. Barium as an element has a 0 charge. All right, when barium is in a compound, we know that barium has a +2 charge. And when potassium is in a compound, in group 1, it has a +1 charge. Okay, so if we look at this, barium goes from barium ion to barium element. And to do that, okay, since it's a +2 over here, it has to gain 2 electrons. Okay, to go from +2 back to 0, has to gain 2 electrons, so that means it is reduced. Okay, potassium goes from potassium element, just a 0 charge, to potassium ion, a +1 charge. So potassium loses an electron, making it, Leo loses an electron, oxidized. Okay. So the little mnemonic helps if you can remember Leo goes Gur, anything that loses an electron. And if you remember, electrons are negative, so losing an electron makes something positive. That's oxidation. Gaining an electron, okay, makes it less or more negative, okay, and that is reduction. Okay, so that's just a quick couple minutes on redox. Again, there are 60 questions on the test. There are a few of these that are kind of fresh that we haven't talked about, but hopefully just looking at this, you can make an educated guess at least. All right. The next few questions are about gas laws. Okay. And remember, our combined gas law is P1 V1 over T1 is equal to P2 V2 over T2. All right. So this asks us pressure, volume. Okay, since pressure and volume are not in a fraction, they are inverse. It's an inverse relationship. If pressure goes up, volume goes down. If pressure goes down, volume goes up. Pressure and temperature and volume and temperature are both direct relationships. Meaning if one goes up, the other goes up. One goes down, the other goes down. So if we wanted to look at these graphically, all right, this one says which graph correctly represents the relationship between pressure and volume. Since they're indirect, excuse me, this graph is a better representation because, as you can tell, as pressure goes down, volume goes up. Okay, and then for the other two relationships, pressure temperature and volume temperature, those are both going to be a direct relationship. If one goes up, the other is going to go up. So that would be B for both of those. Okay. So guess what? You will see one of those graphs on the final, and it will ask you about that relationship. Okay. Now we have some gas laws questions. So let's see how well we remember our gas laws. Okay. So a sample of gas in a balloon has a volume of 2.88 liters and a pressure of 3.4 atmospheres. What is the volume? So what is volume 2 if the pressure is increased to 9.9 atmospheres? So just conceptually, we would expect, since pressure has gone up, we'll expect to see volume go down. So let's see if that is what we actually see. So 2.88. Remember the combined gas law, P1 V1 over T1 is equal to P2 V2 over T2. Remember, you can use the parts of this you want. So, for example, for volume pressure, we just don't include the temperature. We just use P1 V1 equals P2 V2. Okay, so 2.88 times 3.4 is equal to 9.9 times V2. So, let me get my so we can calculate. So let's see, 2.88 times 3.4 divided by 9.9 is equal to 0.989. I can only have 2 sig figs, so this volume would be 0.99 liters. Does that make sense? Absolutely, because pressure increased, volume decreased. All right. Let's see. Okay, here is one that is volume and temperature. So for volume temperature, we're just going to use V1 over T1 is V2 over T2. Okay. So V1 is 34 liters. T1 is 34 degrees Celsius. Do you remember something? Remember, we always have to put our temperatures in Kelvin, which means we add 273. All right. This sample is heated to the point where T2 is 89 degrees Celsius, so we're going to have to add 273 to that also. And then we are figuring out what V2 is. So let's see. So that's 34 plus 273 is 307. So this is 307K. And then 89 plus 273 is 362. So temperature goes up, so we would expect volume to go up also. So let's plug this in. So 34 over 307 is equal to V2 over 362. So I just put these into my calculator. I would do 362 times 34 divided by 307 gives me a volume of 40.09. So that did go up, so that's good. So V2, let's see, I can still only use 2 sig figs. Ooh, so that's going to be, V2 is 40, with a decimal after it, liters, or 4.0 times 10 to the first. Okay, if you want to do scientific notation, but either you should know that you might see either one of those. Okay. Number 40. A sample of gas is in a rigid container. What that means is the volume is constant. Under 0.53 atmospheres of pressure with a temperature of 340 Kelvin. What is the pressure if the temperature is cooled to 200 K? All right, so let's see. So we have P1 is 0.53 atmospheres. T1 is, let's see, what is T1? 340 Kelvin. Nice that it's already in Kelvin for us. We are looking for P2, and T2 is 200 Kelvin. All right, so temperature is going down. We're going to expect the pressure to go down also. So we're going to do P1 T1 over P2 T2. So 0.53 over 340 is equal to P2 over 200. Okay. So again, I cross multiply and divide, so I'm going to do 0.53 times 200 divided by 340. I get 0.31176. So let's see, 2 sig figs. So I can have 2 sig figs. So P2 is going to be equal to 0.31, and that is atmospheres. Okay, so does that make sense? Temperature went down, pressure went down. Good deal. All right, let's see what's on the next page. I think there's a couple more gas laws that we will work through before I stop this video. We'll just get all of the gas laws out of the way. All right, how many moles would fill a 2.1 liter container when the temperature is 25 degrees and the pressure is 1.5 atmospheres? Notice that we don't have any changing conditions and we have moles. So this is going to be the ideal gas law, PV equals nRT. Okay, so how many moles? So we need to kind of spell it out. We've got volume is 2.10 liters. Temperature is 25, but we can't use 25. We have to make it Kelvin. So that is going to be 298 Kelvin. The pressure is 1.5 atmospheres. And remember, R is 0.0821 liter atmospheres per mole Kelvin. All right, let's plug this in. So P, so 1.5 atmospheres times V, 2.10 liters, is equal to, N is what we're looking for, so N times R, 0.0821, I didn't leave myself enough room, times nRT times 298K. What a mess. Okay, so let's plug this in. So I'm going to do 1.5 times 2.10 divided by 0.0821 and then divided by 298. So this tells me that I have 1.1287. How many sig figs? 2 sig figs. So I have 0.13 moles. Okay. I will give you R. R is actually in the test booklet. All right. Number 42 is a partial pressure question. Okay. Remember that Dalton's law of partial pressure says that the total pressure is just equal to the sum of how many ever substances there are. So you combine the pressures and add them together. That's just going to give you the total pressure. Okay. So this says 3 gases, hydrogen, oxygen, and nitrogen, are in a container that has a total pressure of 3.5. So I'm going to do 3.5 atmospheres. Is going to equal, if the partial pressure of hydrogen is 1.2 atmospheres and the partial pressure of hydrogen is 1.0 atmospheres, what is the partial pressure of nitrogen? I'm just going to do N. Okay, so all we got to do for this one, this is easy math, is take 3.5 minus 1.2 minus 1. That gives us 1.3. So the partial pressure of nitrogen is 1.3 atmospheres. Okay. Now this next one, number 43, has a little bit of a spin on it. Okay. And that spin, let me get a piece of paper because I need a little bit more room. Okay. The spin is, it doesn't give us the pressures, but it gives us the total number of moles. Okay, so here's what you can do in this case. You can add up the moles. So we have 0.35 moles of nitrogen. We have 0.50 moles of CO2. And we have 0.15 moles of oxygen. And it says that the total pressure is 5.5 atmospheres. And it asks us, what is the pressure of CO2? So here's what you've got to do. You're going to add these up and you're going to look at what percentage each substance takes. Okay, so I'm going to add up all of the moles. So 0.35 plus 0.5 plus 0.15. Okay, so that comes to exactly, I'm going to do 1.00 moles. Okay, now if we think about this, oxygen, or CO2, excuse me, CO2 is 0.5. So CO2 makes up 50% of the gases. What that means is the pressure would be 50% of the total. So if I just do 5.5 times 50%, whoops, 5.5 times 50% is 2.75. So the partial pressure of CO2, let's see, okay, so for this, I can do sig figs, I can do 2.75 atmospheres. And the reason that I can do that is we were adding these, we weren't multiplying them. When we multiply them by 50%, we don't count that as our sig figs. When we add these, we have everything has 2 places after the decimal. Okay, so our answer is fine with 2 places after the decimal, so 2.75 atmospheres. All right, let's see. In the above question, what is the partial pressure of carbon dioxide in millimeters of mercury? So this is just a conversion. So 2.75 atmospheres. Do you remember the conversion factor? 1 atmosphere is equal to 760 millimeters of mercury. Okay, so 2.75 times 760 is 2090. Oh, that's perfect because that's 3 sig figs, which is what we can use. So 2090 millimeters of mercury. Okay. All right, let's see. We've done 43. We've done 44. Oh, electron configurations. How do you feel about electron configurations? So let me pull up my periodic table here if I can find it. There we go. Okay, so what you have to remember once this loads is remember that these first 2 groups are the s electrons. These 6 groups over here are the p block. We have then the middle, the transition elements are the d block. Okay, and we're not going to do anything more. You won't have to do anything greater than the d electrons. Okay, so the first one says, what is the electron configuration of carbon? So do you remember how we did this? We started period 1, so we've got 1, 2 elements, so that's 1s2. Then you go to period 2, 2s2, and we're working our way over to carbon. So over here, this is the p block, so 2p12, 2p6. All right, so let me go back here. So carbon has 6 electrons. So 1s2, 2s2, 2p2. Magnesium. Magnesium is element number 12. Okay, and let's just look at it for the sake of looking at it. So magnesium is right here. So we would go 1s2, 2s2. We're going to go all the way across the p. So 2p6, 3s2. Okay, so hopefully this is coming back to you. The nice thing is they don't have any crazy hard one on the test, so that's good. So we said, and remember the superscripts are going to add up to the total number of electrons. So 1s2, 2s2, 2p6, 3s2. So if I add up 2 plus 2 is 4, plus 6 is 10, 11, 12. All right, finally we have zinc. zinc has 30 electrons. Zinc is right here, element number 30. Okay, so here's where you got to remember about the D block. Remember the D block is the period minus 1. All right, so we would do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then when we hit here, we go 3d. So it's going to be 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 3d10. Whoops. Uh-oh, there we go. All right, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So let's count. 2, 4, plus 6 is 10, 12, plus 6 is 18, 19, 20, plus 10 is 30. Okay, so 30 electrons. Good deal. All right. Ooh, stoichiometry. All right. We like stoichiometry, right? We like that math. I think that was a test that everybody did really, really good on. Okay. So we'll go ahead and do these before I stop and start the next video. Okay. All right. So how many moles of ammonia would be produced by the reaction of 23.3 moles of nitrogen gas? So if you remember our mole map, we can start with grams of A. We can go to moles of A, moles of B, grams of B. Okay, those are your steps. You got to figure out where you start and where you stop. In this case, our given is 23.3 moles of nitrogen gas, N2. And we're asking how many moles, so what we're looking for is moles of NH3. Okay, so we're going from moles of A to moles of B, one step. So I'm going to do 23.3 moles of N2. And this is where we use the coefficients from our balanced chemical equation. So on the bottom, we have moles of N2. Okay, so that's 1. And on the top, we have moles of B, moles of NH3. And that's 2. So if we take 22.3 times 2, our answer is 46.6 moles of NH3. All right. Next question is, if 328.4 milligrams of hydrogen reacts with excess nitrogen, how many moles of ammonia will be produced? So one thing we need to remember, if it says excess, we don't consider it at all. Okay, it just means there's enough there that hydrogen is going to be the limiting, it's going to be the one that runs out first. All right, and this one did a little tricky thing again. It gave it to us in milligrams. So before we do anything else, we need to convert from milligrams to grams. So we're going, let's see, so we're starting with milligrams. So technically we're going from eventually grams of A, how many moles, to moles of B. Okay, but we got to get to grams first. So 328.4 milligrams of H2. Okay, we need to go to grams. So 1,000 milligrams is 1 gram. Then we get into our stoichiometry. So we want grams of hydrogen on the bottom, okay, and moles of hydrogen on the top. So 1 mole of hydrogen is, hydrogen's molar mass is 1.01, so 2.02. Okay, and then we need to go to moles of ammonia. So we have moles of H2 on the bottom, and this is where we get our coefficients. So moles of H2, there are 3 of them, and moles of NH3 are 2, so 2 moles of NH3. And we only need to go to moles, so we do not need to do the molar mass of ammonia for this problem. So let's see, 328.4 divided by 1,000 divided by 2.02 times 2 divided by 3.10838. I can use 4 sig figs, so 0.1084. 0.1084 moles of NH3. All right, the next one is a limiting reactant. So this is the granddaddy of stoichiometry. The good news is it's only going to ask you for the limiting reactant. It doesn't make you calculate. We don't ask you for the excess, so that's good. I think that's a time-saving thing because I know you only have a limited time to do this test. All right, so if 25.6 grams of N2 reacts with 32.8 grams of hydrogen, how many grams of ammonia will be produced? So remember, this is where you got to do 2 gram to gram conversions. Okay, so you start, we're going to do 25.6 grams of N2. We're looking to go to grams of NH3. Okay, so the first thing we need to do is we need the molar mass of nitrogen. So nitrogen is 14.01, so 28.02, that comes from the periodic table. That is 1 mole of N2. The next step is our mole ratio step. So we have moles of N2 on the bottom, moles of NH3 on the top. Balanced chemical equation, N2, there's only one of those. NH3, there are 2. Okay. And then the last step for this one is we need the molar mass of NH3. So 1 mole of NH3. Oops, not NH4, NH3. And nitrogen is 14.01. Hydrogen is 1.01. Okay, so 14.01 plus 1.01 times 3 is 17.04 grams of NH3. All right. I'm just going to set up the other one. We're just going to calculate them all together. All right. So I'm going to do this other problem. I start with 32.8 grams of H2. 32.8 grams of hydrogen. We're doing the exact same thing. We're going to grams of ammonia. So molar mass of H2 is 2.02 grams. That is what 1 mole of H2 is. Next step is mole ratio. So we have 3 moles of H2 on the bottom and 2 moles of NH3 on the top. And then we need to convert to grams of NH3. And that's the same. We did the molar mass, 17.04 grams of NH3. All right, let's do some calculating. All right, 25.6 divided by 28.02 times 2 times 17.04, 31.1, we're going to use 3 sig figs, so 31.1 grams of NH3. The second one is 32.8 divided by 2.02 times 2 divided by 3 times 17.04, 184.5. Oh, no, 3 sig figs, so 184. Okay, now remember, when you do this with the limiting reactant, okay, your theoretical yield is going to be the smaller of the two numbers. Okay, so your answer is 31.1 grams of NH3 will be formed. To figure out the limiting reagent, you look at what you started with. So when we ended up with 31.1 grams, we started with nitrogen. So N2 is our limiting reactant. All right, I'm going to stop there just so we can kind of chunk these videos. And let's see.